Okay, now I'm going to add back this function here that calculates so this one calculates from the index, the 1D index, the Merton index, it calculates the 2D IX. And it's doing the opposite operations of what was in the previous one. So now it's adding to the IX2 in the same way that it was adding to the index in the original one. So okay, just for consistency, let's call this index. And now, okay, let's see if this returns for index I. Yeah, why don't we just use index I for now? No, we don't want to modify the index I. Let's put this inside index 2 so it doesn't break anything. Okay, so now what this is doing is it's trying to generate the index from, or IX from the index. So let's see if that's possible. Okay, I'm going to put this inside the loop and before the print so I can see it print. Okay, so before this operation, IX is already 0, so I don't need to make IX equals 0. And D is already defined somewhere, I think, or no. So I need to define D equals 0. I'm missing a semicolon here. Okay, while index 2 is greater than 0, meaning while we still have bits to process, this will take the current bit and shift it this many number of levels and add it to the IX appropriate dimension. Again, I think this will add it to the wrong dimension unless we have like 1 minus D here. Okay, let's see if this prints the proper IX. So I'm going to print IX here. This is from what we generated. GCC step 3. So this is going back from index to IX. Okay, so it looks okay. I think 0 and 3 was 5, 6 and 2 was 44. So we started with first determined IX here, then from IX we determine the index, and then from the index we do the other operation which sort of de-interleaves the bits into the two IX components. I did 1 minus D here so that 0 becomes 1 and 1 becomes 0 because the X and Y were switched in the this definition. So, okay. And then, yeah, this is just same bit shift operator, same bit extraction operator, and very, very similar operation to what we did in the get index. Maybe I'll call this one get IX so that, and turn it into a function. And now we have the ability to go back and forth between the IX and index. Right? So I'm going to turn this one into a function. Get IX the input would be index. Yeah, and we don't need the 2 here anymore because we are going to input the index now. The level, I think we initialize anyway inside the code like this. Okay, now we have a function that calculates the IX from index. Let's move this to the beginning of the code again. Okay, can everyone see this code? This is get IX. So first we set level equals 0, and level gets incremented every time the dimension. So D goes from 0, it starts from 0, and then it gets added 1, and then when it becomes 2, then you do this operator, and then it gives you back 0, so this becomes 0, and then it becomes 1 again. So this operator actually produces 0, 1, 0, 1, 0, 1. And every time it goes back to 0, that means it's at the next level, so the level is incremented. So it's like a way of making D go 0, 1, 0, 1, and making level go from like 0, 1, 2, 3. But only if the D has gone from 0 and 1 again. So this is like a strange way of getting dimension to go 0, 1, 0, 1. Okay, so now this function is called get IX, and we will demonstrate if it works like this. Oh no, how do we return there's no return value. We need to return the IX actually. So yeah, let's make it return the IX value. Yeah, we need to initialize the IX because we don't know if it's 0 when it comes in. Okay, so IX, it's now returning IX. Now this should return the same results. So when we do GCC, when we compile and run, yeah, so now it's giving back the same result. Okay, now we have the 2 components for doing the interleaving and de-interleaving of the bits. We can find the Morton index, and we can also, from the Morton index, we can find the 2 pair of index now. Okay. So now, let's actually form the tree operation. So now I think we can do the where is it? The offset calculation for generating the this one. Okay, so now let's do the tree construction, because now we are able to generate these numbers. We need to sort the indices, and then we need to move the x, y, and q. Well, q is the same number everywhere, so we don't maybe need to move it. But we need to move x and y so that we need to move x and y so that they are in this order. So let's do that part. Does anyone have any questions up until here? Everyone is okay with the index generation and going back and forth between the two-dimensional and Morton index? Okay. So now let's move to the index manipulation. So now, once we have the index, let's remove the printf here, and yeah, we don't need the get ix for now. Okay, let's generate. First we can sort. Let's see. Does I wonder if we can use the sorting. Is there a sorting for? Let's see if this works. I don't know if the. No. Okay. Math. Yeah, maybe we need to have a sort. Q sort. No? Too few arguments. You need the size and size of okay, I think this should be okay now. No? No, there's no such thing. Comparison functions. Oh, I need to write my own. Oh, really? What if I don't put anything here? Is it? No, it needs a comparison function. Okay, this is not very convenient. So it seems like I have to write my own function that tells what's large and what's small. Okay. So now I think this should work. Okay, but now since I haven't printed anything, I don't know if it's working. Let's see if it's working. Print index. So let's see if it's been sorted. So maybe we can print before and after. So before, yeah, it's sorted. Okay. So you see here, I'm printing here before the sort, and it was 5, 44, 32, 23, so it was not sorted. Now, after I pass it to qsort function, is everyone able to run qsort in your, maybe some C compilers don't compile this. Is everyone okay? Qsort? Just put index here and n, size of int, and something that tells you what is large and small. Then if you look at the output, index here has been sorted so that it's now in order. It's in ascending order, 5, 23, 24. So now it's sorted. Now what we need to do is to make sure that the x and y are also sorted according to this order. So when we print x and y here, they will be corresponding to the index that's sorted. So now let's try to see if we can do that. In the meantime, in case you missed what compare ints is doing, because I did it too fast, it's doing something like this. I just copied this from the other website. And let's see. So I need to sort x and y, x according to the new index. Or no. Yeah, I need this to return the permutation index, which I don't think it does. Does it? Qsort. No. Yeah, it doesn't give me back what I want. So what I want is how to move the x and y. Okay, so this sorting technique is not giving me what I want. So I'm going to copy over some function I have that has this feature. And okay, so I'm going to define my own sort because the one that's provided is not giving me what I want. So this is a radix sort. The one that I called earlier was Q sort, which is a quick sort, but this one is a different sorting algorithm called the radix sort. It's better for this FMM index finding because when you have many same indices, then radix sort is much faster. So in our case, we have many identical indices because many particles belong to the same cell, and for the same cell, the cell index is identical. So if you have something like that, then it's much better to use this order n radix sort. It's a bit longer, but I think you can. Okay. Okay, so now this function takes in key value and size. Key is the index. Oh, sorry. Value is the index. Key is some array of integers that will tell you how the numbers are permuted. So this is what was missing in the previous method. Bit stride. Oh, okay. So this code is written in C++, so I need to change it so it's in C. Okay, so everything else should be the same. Also, maybe this is not good in C. Okay. Let's see if this works. So I'm just going to change this to radix sort. And I don't need any of this. And I need some permutation index. So this is what I need to sort the x, y, is the numbers that are originally, so these numbers are originally in order, but then when I actually do the calculation, they will become, so I'll just put here, number from, and then after I do this, you'll see what's going to be printed. So I'll print this number and so that you can see what's happening. So before and after the sort, this number changes into the order that it was moved. Okay. 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 Okay, now step 3.
Smaller size S.
There's something, what? It's smaller size?
Yes.
Radix sort, conflicting types. No, they're both integers. Integer, integer, integer. Why does it say it's constant signed? Too few arguments? Okay, maybe it's like conflicting with some other function name. Okay, so now, why did the index turn to all 0? Oh no, the permutation turned to all 0. So the permutation should actually be returning key. Oh, maybe I input it the other way around. Index and permutation. Okay, so the value gets destroyed. I see. Well, that's okay because all I need is a permutation actually. So if I do this, it should give me the correct. But not if it's completely destroyed. Let me save index in some other array so that it doesn't get destroyed. Index 2 is index. Okay, so now this should return what I want. Yeah, okay. So what I have now is the original order was this, and now it's sorted. I originally used a quicksort, but it wasn't returning this permutation thing that I need. So what this permutation is it looks like this. It's 0, 3, 5, 2, 8, 9, 7, 1, 4. So what is this number? This number is something that if you use, like I'm using now to, like here, if you index something with this permutation, it actually returns it in the sorting order. So this index 2 is not sorted. I just saved it up here. It's not sorted, but this permutation actually permutates the values in the order that produces this sorted outcome. That's why I needed this. Now, if I apply this to x and y, I will get the x and y in the order that I want. So this permutation is actually what I was looking for, not the sorted index itself. I want to know how I can sort to get everything in this order, not just the index, but also the x and y in this order. So now I will print x and y also to see that they are. So if I print x and y here, they should be in the order of this index. So that will be different from the order here if I print with the permutation. Okay, now step 3 will give me, so see this x and y are now in a different order. So, well, the first one is the same because it's 5. But then this 23, now the x is from the one that says 23. It's this one. This one is now in the second place. And now the 24, which was down here, the 0.35, 0.57, is now up here in the third row. Okay, so yeah, now we have x and y and the index in the order that we want. Actually, but we don't want to keep using this permutation. So what we want to do is to actually substitute into a new x and y so that we don't have to okay, so let's create a new set of x and y's that's already sorted. So we will say x is now x permuted value. So with this new x and y, we can get the new. Oh, actually, since I don't want to use x2 and y2 everywhere from now on, why don't I just use it as a buffer? So I'll first buffer x and y here, and then along with this index, what I will do is say like this. So this new index, so I first put everything in 2 so that I can later use this index 2, x2, and y2 to permute the values. You see why I can't just do x and y permute equals x and yi, because inside the loop, I will modify some part of x, and then that part gets referenced later on, and then it sort of breaks. So you can't do an in-place permutation. So that's why I needed to define a new x2 and y2 here, so that while it's permuting, it has, the new x is intact and it's not referenced while it's still permuting. So you need to first create a buffer, copy everything into x2 and y2. And oh, sorry, I think this definition needs to be up there because it's being used before it's defined right now. So this should be defined somewhere up here so that it... Okay, so now we have... I don't need to use this x2 perm thing anymore. I can just say index I and xi and yi. This should give me what I want. Yes? Okay. Okay, let's just check if that is true. Yes, okay, so it seems like everything is working. Okay, so now what we have, we're almost ready with the tree, because now all the points are sorted according to the permuted order, and we have these values in order. So now we need to calculate to make the tree. If you remember from the slides, now we have this, okay? It's in order, and x and y are both sorted according to this value. Now we need to calculate the offset. So where the starting point from 0 and 1 and 2 is in terms of the number of the x and y. Okay, so how do we do this? We first need to create a new loop for I and then we need to have some counter that's initialized here that keeps the value. So if this counter is not equal to the current index, and since the index is in order, while it's the same, it will not call this part of the function. But if it isn't, then it needs to have, let's see, so what I want is to create an array that says offset, and its size I don't really know yet, right? Because it depends on how many identical duplicate entries we have. So until I look at that, I don't know. So I also have like a duplicate entry or no, like another counter, let's say, that tells me every time I have a different entry, it will give me this number. Okay, so I think this will give me all the offsets I need. And this. So what this is doing here is I'm first looking at all the indices, these values here, 2, 5, 23, 24, 32. So, well, the only duplicate entry we have now is 44. So we need to increase the number of points for this to actually make a lot of sense. But let's pretend that there are many duplicate entries. What will happen is it will loop over. It starts from everything being 0, 0, 0, and IC is 0, index is 0. So, actually, the initial offset should always be 0. So I should actually start offset 0 should be. Everyone knows that offset 0 is always 0 because the initial cell always starts from offset 0. Okay, and then in that case, ID should start from 1 because so whenever IC is different from the initial index, so the initial index is now 5. So okay, IC should start from the initial index, otherwise this doesn't make sense. Okay, so until it becomes different, it won't call this part. So it will just keep moving on, and I will keep increasing because of this loop. And then once it hits the place, it goes to the next cell, the index will change. And when the index changes, it's no longer IC. So then you need to calculate the offset of that point. And that I at that point is the offset of this next cell. So I can either use ID here, which is like a counter that counts the number of boxes. So ID, the count of ID will tell me how many boxes I have. It's initially 1, but every time I encounter a new box, it will be incremented. So it will tell me how many boxes I have here. If I apply this to this thing, since this has one duplicate entry here, in total I should have 1, 2, 3, 4, 5, 6, 7, 8, 9 different boxes. So ID should be 9 if I execute this. So let's check if ID is 9 to see if this is working. If this returns, okay, so let's stop printing here. I want to know if this ID is working. So I just want to print ID. And hope that it prints 9. Oh, good, 9. Okay, so what this is doing is it's just counting the number of boxes and duplicate entries and calculating the offset. So let's now print the offset, which won't make too much sense if there's only one duplicate entry, but still, it's good practice. So maybe I'll just print inside this loop here. Also, along with I will print the offset of ID. Or maybe I'll just print ID and offset ID. Okay. No, this is not what I want. Do I need to initialize? No. Why is there a strange number in offset? it's behaving in an unexpected way. No, maybe it's because it's not defined when I'm printing. So this is when it's defined. Oh, sorry. So ID is incremented here, so I need to print before it's incremented, otherwise it's printing something that hasn't been defined. Okay, so now you see that it's not very interesting because until here, until the end of the calculation, it's just incrementing every time because index is always different. So it's just calling this every time, and the offset is, starts from 0, but it goes 0, 1, 2, 3, 4. So now a more interesting test case can be constructed by actually increasing n. So we've parameterized this code so that just by changing n at the beginning, we can increase the number of points a lot. So if we increase this to 1,000, we will start to see many duplicate numbers, right? So now it makes a little bit more sense because since there are many duplicate entries, now we have, so when it's 0, it's 0. The offset is 0 at the beginning. Then for the first cell, because the cell number 0 contains 20 points, the first offset of the first cell is 20. Then cell number 1 contains 12 points, so the offset for cell number 2 is 32, and so on. So now it makes more sense when you have more points. Now we have the offset. So now how do we use this? Now this number here is actually the cell number. So it goes from 1, it's continuous because we're incrementing it one by one. We just need to loop over this number to retrieve all the cells. For each cell, we have been storing the unique index of each of the cell. So this is actually the, so we have stored the unique offset of that cell. So if we wanted to access all the particles inside cell number 9, then we need to loop from 149 until 159, and then we can access all the points inside that cell number 9. And because we sorted over here, because we are sorting x and y in the same order as the index, inside this cell, all the x and y index are continuous. So you can access them in a continuous way. They're not randomly distributed anymore because we permuted them in the order of the index array here. So now we have the tools to access all the points inside a given cell. The remaining task is because this is still accessing with ID, ideally we want to access this with the Morton index, not ID. And actually this index here is the Morton index, right? We calculated this Morton index in the previous parts. We calculated, up here, this index is actually the Morton index. So if we assign down here this index, instead of ID, if we put here index I, then we can actually calculate the offset, or we can actually retrieve the offset from the Morton index. Maybe that would be even better because we usually access the cells with this index, not this continuous index. So let's change that. And then we are ready to do all the P2M, M2M, and M2L kernels, and we still have 1 more hour, so I think we can do everything. Okay, so yes, should we take a break? Okay, so yes, I will do one last change of this to index I, that's all. Well, maybe I don't need to change the print part. Okay, so the code right now, this is step 3. Let's save step 3 like this, and so yeah, step 3. This won't print anything because I removed the print, but check that step 3 runs. Okay, so step 3, we have now constructed the tree, basically. We now have a way to access all the numbers inside each cell and its parents and children by dividing by 4 and multiplying by 4. And we can also go back and forth between the 2D index and the 1D index, and so we can find the neighbors using this code. And step 4 will be maybe finding, we can either do the P2M, M2M, L2L, and L2P kernels first, and then do the neighbor finding, and then do the M2L and P2P kernels. But anyway, we will leave step 3 like this. Okay, we can continue in 10 minutes? 12:10. Okay, thank you. Oh, I'll leave the code on the screen, so if you miss something, just tell me where you want me to show. I will have it showing on.